Hi everyone, this is Mark Weitzman. Welcome back to the second video on problem 4 of chapter 2 of Weinberg's The Quantum Theory of Fields, where we're showing that in the first video we showed that the energy momentum 4 vector commutes with all Lorenz transformations. Now we're going to show that the Pauli-Lubansky pseudovector also commutes with all Lorenz transformations. And this is the definition of that Pauli pseudovector. So what we want to do here, using the same technique as I showed last time, is we're going to start the same way. I'm going to try and be a little bit more concise in my notation right now. But we're going to have U, and U basically is, U of, just to review, lambda comma A. This is the unitary operator which represents the Poincare transformation given by a Lorenz transformation lambda and a translation A. So in case I didn't make that absolutely clear, we'd have something like x prime U is equal to lambda U nu x nu plus A mu. And as I mentioned, it's a 10 parameter group. So with this transformation, we associate this unitary operator. And we want to show that this vector commutes with that unitary operator. So what we have to show, let's use this long line here. We're going to have U, I'm going to leave out the lambda comma A. I'm going to have U, W mu, U inverse. And then we're going to do that same thing with folding in identities. We're going to write this as U, W mu, U inverse. This is the identity, that's why we put in U inverse U, W mu, U inverse. So we, as you can see, we're basically going to compute the same thing twice. This and this. It's the same thing, it's just, when we get this, we lower the index, or we can get this, we raise the index, either way. So let's now compute U, W mu, mu inverse. This is equal to, substituting that definition in here, we're going to get a mu And now, since we have these two things, we have to fold in more U's. And remember, as I said before, the epsilons and the etas and the lambdas, when you put indices on them, they're just scalar numbers, so you can take them out. So this is equal to epsilon U nu rho lambda. Now I have U J nu rho U inverse. And I have U P lambda U inverse. Okay, now we can use these two things on each of those, there and there. So this is going to be epsilon mu nu rho lambda, capital lambda, alpha nu, capital lambda, beta rho, J alpha beta minus A alpha P beta plus A beta P alpha. And then I have lambda small lambda gamma P gamma. So we just have to, we're going to have two expressions like this. It looks messy and everything. The key thing when doing these things, don't expand. Don't multiply these things out. You should see that these two are going to go to 0. It's not obvious now, but we'll see that these two things go to 0 and we won't have to worry about them. And then we'll have various epsilon identities and various Lorenz transformation identities, and we'll end up just getting a J with a P, which is the definition of the W. So let's work it out. So I'm just going to rewrite that completely. I'm just going to, I think we know what the problem is now. Sorry about that. So I'm taking that last operator and I'm bringing it inside for reasons that will be clear. So now you see that there's like two P's and this is symmetric, and hopefully right now we can't do it because it got beta gamma here. I don't have beta gamma here, but when eventually we'll find out these two terms drop out. Okay. Now, I need to derive an identity, which is not hard, but is the key to solving this problem. So I'm going to do that right over here. This is a well-known identity that you should have learned in your linear algebra or prior physics classes or whatever. Right now I'm thinking of the capital lambdas, the Lorenz transformations, simply as matrices. So this identity will hold for any matrices. Okay, so if you've never seen this before, I suggest you somehow convince yourself of it. Thinking of lambda as a matrix, what you're doing is, the easiest way to think about it is, let's test it for one value here. So let's make this like 0, 1, 2, 3. Okay, epsilon 0, 1, 2, 3 is 1. So what it's saying is that the determinant of lambda is we have a matrix and we're multiplying, we're expanding on the columns. You know, this is the 0 column. And we're taking an element of this column, like here, and multiplying by an element of this column, then an element of this one, and then this one. And we're just getting all the products in the determinant. This guarantees we have the right sign. And this guarantees if we permute the columns, we're also going to get the right sign. So I suggest you verify that it's an identity that will prove useful in group theory and various other things. But right now I just want to derive a very simple corollary of this identity. If you remember over here, what we have is we have 3 lambdas. So what you can do with these right here, you got the epsilon symbol and 4 lambdas on one side. Forgetting about the determinant, there are no lambdas on this side. But you can move these lambdas to the other side using the basic properties of Lorenz matrices. Now, you can do these with like SO3 rotations and unitary matrices, but the lambdas, you know, lambda is SO3 comma 1, you know, special. It has determinant 1 or plus or minus 1, 3 plus signs on the metric and 1 negative sign. So it's a little bit trickier. So it's best to just go back to first principles and derive this, which is what I did. So first thing I do is I'm going to multiply both sides of this equation by the same factor, and you'll see what that factor is. So I'm going to get epsilon alpha beta gamma delta lambda alpha mu lambda beta nu lambda gamma, small lambda, lambda del omega. And then I'm going to multiply that by lambda kappa tau, eta omega tau. And I'm going to do the same thing on this side. Now, what do we have here? We have, remember these identities where you had 2 signs on the things? We have it here. We have eta omega tau, lambda omega tau. So this thing just becomes eta del kappa. Okay? And then when I apply eta del kappa to this, I'm just raising the index here. So I'm going to end up getting epsilon alpha beta gamma kappa lambda mu alpha lambda nu beta. Notice these 3 always sum on these 3. Lambda gamma lambda not sure I did that right. Hold on 1 second. Okay, yeah. And this is equal to epsilon mu nu lambda omega determinant lambda k tau eta. Well, okay, so here we're raising the tau indices with the omega, so I'm just going to make that kappa omega. Okay. Now I'm going to do 2 things at once, because this is kind of boring. First thing I'm going to do is lower the kappa index on both sides of the equation. So I can do that. And then I'm going to switch the first index on the with the fourth index on the antisymmetric symbol. That introduces a minus sign, but I'm also going to do it here. So finally I'm left with epsilon, kappa, alpha, beta, gamma, lambda, alpha mu, beta nu, gamma lambda is equal to epsilon omega nu lambda Well, what I want to do is I want to switch mu with lambda. Well, I'm not going to worry about it. Omega nu lambda mu, determinant of lambda. That should be the whole lambda. Times lambda. Remember, we lowered the kappa. This is basically the identity that I want, except now I just want to switch mu and nu. And I do one. That's going to not change anything. I'm going to do, that's one sign, two signs, and then three signs. I might have screwed up a sign here, but I'm going to do it anyway. U nu lambda. So I want this is the identity that I want. Okay. So this will work perfect for this over here, because it's the same thing. We're summing on nu, rho, lambda. These, we're not going to touch this, and so on. So this thing goes down the same. And we're going to get epsilon, omega, alpha, beta, gamma, just applying this identity to this equation. Lambda, mu, omega. I get J alpha beta minus A alpha, P beta, P gamma, plus A beta, P alpha, P gamma. Okay. Now where will we want? Because here, this is symmetric, but this is anti-symmetric, so this cancels. This is symmetric in alpha and gamma. This is anti-symmetric in alpha and gamma. So this cancels. So I'm just, yeah. I might have screwed up that derivation or left out a sign, but I'm not going to worry about it. And by the way, there's a determinant of lambda in here too. Okay. So I've got rid of these two terms, and I'm left with just this. So now I can just do both of them. U lambda comma A, W mu, u lambda comma a inverse. It's just going to be the product of this. The only index that's going to stay the same is the mu, and everything else is going to get a prime on it. So what we get is we get epsilon omega alpha beta gamma, just like we have here, lambda mu omega j alpha beta. I left out that p gamma again. J alpha beta p gamma. There's a determinant of lambda. I'm going to put this on the end from there. And then I get the second factor over here. The only thing here I do differently is I raise the mu index. So I get epsilon, and I change every other index, every other dummy index, I just put a prime on it. W prime, alpha prime, beta prime, gamma prime, lambda. Instead of the mu lower, it's now upper, lambda mu, omega prime. Okay. Obviously, we're going to get another factor of the determinant of lambda, and the determinant of lambda squared is 1 for a Lorenz transformation. That just comes from the group. If you remember this, if you take the determinant on this equation, you get -1 here, and you get -1 and -1. So the determinant of lambda has to be equal to -1. I'm sorry. The determinant of lambda is going to be plus or minus 1. The determinant of lambda squared is always going to be 1. So I'm going to have that, which is 1, but I don't need it anymore. And now I got my J's here. J alpha prime, beta prime, p gamma prime. Okay. So that formula over here, we're almost done. The main thing we have is we have this alpha mu omega over here, lambda, I'm sorry, lambda. And we have the lambda mu omega prime. Since the mu's are the same, this just becomes eta omega omega prime, which raises the omega prime index. So we're left with u w mu u inverse is equal to epsilon omega alpha beta gamma lambda mu omega j alpha beta p gamma, and then we multiply that by epsilon w alpha prime beta prime gamma prime lambda mu, I don't know why I read it. Oh, okay. Okay, I shouldn't have any lambdas. I took those out. Okay. The only thing that the product of the lambdas did was they raised that omega index. Replaced omega prime by omega and raised it on the second term. So I have that j alpha prime, beta prime, p gamma prime. And this is the definition of w omega, which is equal to, w mu. So we've shown that u times w squared is equal to w squared times u, or the commutator of u with w squared equals 0. Okay, so sorry it's a little messy and I went a little fast at the end, but I think you all have the idea right now. The basic idea is to fold in identities of U, so you can use these two identities, and then you need an identity with the antisymmetric symbols and the lambdas. Basically, the antisymmetric symbol times 4 lambdas gives you the determinant, and if you want to bring a lambda to the other side, you just do a multiplication and it goes to the other side. Thank you very much. I'll see you on the next video. Bye-bye.